I'll just show one last diagram because that diagram is what Euclid used in his proof of a Pythagorean theorem. It's actually a little more complicated, but it is very interesting. This proof is by Euclid. When we say Euclidean geometry, that's the geometry named after Euclid. When we say Euclidean distance, that it's all based on the work of Euclid. Anyway, Euclid says that if this is a right triangle, we call this A, this is B, this is C. What he did was to construct a square on the side of A and a square on the side of B and a square on the side of C. Okay. He wanted to demonstrate that if you add this square and this square, you will get this square. So I'll just give you a clue. And you can take this home with you. If you're waiting for your friend and your friend is not on time, then what you can do is take out a piece of paper and try to prove the Pythagorean theorem. In that case, you do not kill time. You make use of your time. What Euclid did was to drop the perpendicular to this side from this point. And he showed, using some geometry, that the area of this rectangle is actually A squared. And he showed that the area of this rectangle is B squared. And that is what he did. He just used the theorems of geometry. We will not prove this in class. But as I said, I've left it to you. So that you will have the pleasure of doing it during your free time, so that you do not kill time. Now, as I said, the Pythagoreans were interested in the relationships of numbers. The Pythagoreans were interested in how to form perfect squares. So, Edu, can you tell me how to form perfect squares? By perfect squares, I mean the numbers 1, 4, 9, 16, 25.
We can form a perfect square by multiplying a number by itself.
That's correct. A perfect square is just the product of a number multiplied by itself. So 1 squared is 1. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. What is 15 squared?
2 to 5.
2 to 5.
Wonderful. 2 to 5. What is 17 squared?
269.
269. 6.
9.
289.
It's 289. 289. 289. Anyway, here's another thing you can do when you're waiting for your friends who are late. You can look at the squares, because the Pythagoreans, many years ago, also contemplated the squares. 1, 4, 9, 16, 25, 36, 49, etc., etc., etc. We will never run out of squares. But all these squares have one thing in common. The first square is 1. The second square is 1 plus 3. The third square, 3 squared, is 1
plus 5.
1 plus 3 plus 5. The fourth square is equal to 1 plus 3 plus 5 plus 7. That's 4 squared. Right? 5 squared is 1 plus 3 plus 5 plus 7 plus 9. 6 squared is 1 plus 3 plus 5 plus 7 plus 9 plus 11. Do you see a pattern here?
Yes.
And now who shall I call? Joseph?
As I observe, square perfect square numbers is equal to the sum of consecutive
Two.
odd numbers.
Yes. So Joseph observed, as the Pythagoreans observed many years ago, that a perfect square is actually just the sum of consecutive odd numbers. In fact, 5 squared is the sum of the first 5 positive odd numbers. 6 squared is the sum of the first 6 odd positive numbers. So what is n squared? If the pattern continues, then
One dot 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 n.
In consecutive odd numbers.
n squared, the square of n, must be the sum of the first n consecutive odd numbers. No? Wonderful. The Pythagoreans noticed this. No? But is it true? At least we know it for the first 6 squares. How about 7 squared? 49. Well, you can add.
Yes.
How about 8 squared?
64.
64. That's 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus
15. 15.
17. Did you actually perform the addition?
No. Until 15.
Until 15.
Kasi
Yeah,
it's
the first 8 odd numbers is 1 up to 15. How about 10 squared 100?
So up
19.
Up to 19. 1, 3, plus 5, plus 7,
What's the number minus
9.
plus 9, plus 11, plus 13, plus 15, plus 17, plus 19.
Yes.
Well, you can add. You can add using your pen and paper. You can use your calculator. And you will see that if you add all these numbers, you will get 10 squared. How about 11 squared? What I'm saying is that we can see that the pattern is true for these things. But can we see it for the general odd number, for all numbers?
Not yet.
Not yet. No. So we need a way of understanding why this pattern is true. So the Pythagoreans, just like Joseph a few minutes ago, noticed that perfect squares are sums of consecutive odd numbers. No? But we need to convince ourselves. And one way mathematicians convince themselves is, again, by proving a statement or by looking at that statement from another point of view. And we will do it visually. 1 squared can be just, this is the most simple perfect square. It's just 1. 1 plus 3 is 2 squared. And 2 squared can be represented by 4 circles arranged in a square, right? And can you see the 1 plus 3? This is 1 plus 3. Now what happens if we form the next perfect square? 1 plus 3 plus 5 is 3 squared. And 3 squared can be represented as an array of 9 circles. And we can count those circles by looking at the L-shaped rows. 1 plus 3 plus 5. And we do that again for the next perfect square. 1 plus 3 plus 5 plus 7 is 4 squared. And that's 1 plus 3 plus 5 plus 7. Now do you see how the pattern unfolds? How about 5 squared? How do you form the next perfect square?
You just add one circle.
Well,
Add a
we just
circle of
add
one
another
there.
L-shaped row.
Yes.
And that L-shaped row will have 2 circles more than the last row. So in effect, what we are doing to form the next perfect square is to just add a row that is 2 more than the last. So the next odd number. And you see how this will produce all those perfect squares. To go from one square to the next square, all you have to do is just simply add the next odd number. So is this more convincing?
Yes.
Yeah. We are able to visualize a numerical pattern, and that visualization allows us to see, to have access to a true statement. You know. It's a wonderful feeling. The Pythagoreans did things like this. You know. And every time they encountered a true statement, you know, they felt very happy. In fact, there's a legend that when they discovered the truth of the Pythagorean theorem, the Pythagoreans, these are the followers of Pythagoras, you know, they celebrated by butchering 100 oxen, you know, or 100 cows. You know, they celebrated. So they had a feast.
Walang magawa.
Can you imagine having a feast because of a mathematical theorem? But that is how important that piece of knowledge was. The Pythagorean theorem evokes a lot of feelings. Erlinda, what do you feel
About the Pythagorean.
about the Pythagorean theorem? Are you happy? Are you sad?
Interesting.
Are you interested? Are you perplexed? Actually, it's a very odd statement. If you really think about the Pythagorean theorem, think about it. What has right triangles, which are everywhere? Everywhere we look, there are right triangles. Right? You know? Or right angles. You know? Every time you have a right angle, you can imagine a right triangle. So we are surrounded by right triangles. All those name cards, you know, are perfect rectangles, which are formed by combining two right triangles. We are surrounded by right triangles. There are infinitely many of them. Now the question is, if you really think about it, what do they have? What do they have in common with that very simple equation, a squared plus b squared is equal to c squared? You know, at first glance, there's nothing. Nothing in our intuition would tell us that all right triangles, you know, actually exhibit a very simple equation, a squared plus b squared is equal to c squared. It is so odd, kakaiba. It is so odd that we only fail to see the oddness because it is so familiar. Sometimes when we see something every day, we don't ask questions anymore. It is so familiar because every kid knows the Pythagorean theorem. You know? And because of that familiarity, it takes away sometimes it takes away the wonder. And there was a writer, his name is Richard Trudeau, who wrote the book called The Non-Euclidean Revolution. This is what he said. No? To me, the theorem of Pythagoras is very surprising. A squared plus b squared is equal to c squared. No? It is surprising because it evokes no visceral memories whatsoever. If you look at that equation, it is nothing. Forget about the Pythagorean theorem. Just look at that equation. There's nothing about it. And yet, that equation is related to every right angle that you see around you. I mean, it evokes nothing, and because the equation is abstract and precise, it is alien. It's not part of my everyday life, unlike right triangles. I can't imagine what such a thing could possibly do with everyday right angles. So when the pall of familiarity lifts, the pall, it's so familiar, forget that it is familiar. Imagine yourself looking at it for the first time. So when the pall of familiarity lifts, as it occasionally does, and I see the theorem of Pythagoras